10 prisoners are given one chance to escape. They are standing in a queue, facing in one direction, each of them wearing a hat that can be either black or white, so that a prisoner can only see what is in front of him, and not behind, or even his own hat. Starting from the last prisoner, the one able to see all others, and without communicating in any way, they're all given a chance to guess the color of their own hat. If they get it right, they escape. Otherwise, they're destined to rot in prison. They have 1 hour to discuss a strategy before the game begins. How many can be saved? And here we go with the first challenge. If you haven't watched the strategy videos already, make sure you do, as we will try and build a solution from there. If you are familiar with riddles, you might have a clue on how to proceed. But my plan is really to start from scratch, assuming we have no idea how to tackle this. Well, actually the idea is to use the strategies, so let's look at the general ones first. Number 1. Use the information contained in the text. Can we find some natural, even obvious implication? If we imagine how the game is going to play out, all prisoners will be on a line, and after each of them received, without looking at it, the hat, the last in the line will have to guess. Now, he has no information whatsoever, as the number of black and white hats is completely random, so he will not be able to infer the color of his hat. The best he can do is to help the others. So we know that at least one will not be able to save himself, but we also know that he can't die in vain. Number 2. Develop an intuition of what is going on. What is hard about this problem? Well, the issue here is that each prisoner has as an absolute first priority to save himself. Then, to help the others save themselves too. If we split the prisoners between helpers and rescued, we can easily imagine a strategy where the last just says the hat's color of the one in front, so that he can save himself. The one after will do the same, and so on. By the end, 5 will be saved. But obviously we want to do better than that. Number 3. Symmetries and invariants. Now, for symmetries, this is a clear example of white to black symmetry. If all hats were swapped, and the prisoners told the color opposite to the one of their hats, the game would be exactly the same. There is no intrinsic difference between white and black hats. Invariance instead is something that we will look for while building the strategy. Things that don't change during the game or change in a very predictable way. Number 4. Solve a simpler version of the problem. We can already see that this is going to be huge. Talking about 10 prisoners might make the problem much harder, but what about 2 prisoners, or maybe 3? Can we spot something which we're then able to apply to the case with 10 prisoners? Worth trying. Number 5. Look for alternative formulations of the problem. We will skip this one, I'm not really sure this is applicable in our case. Number 6. Draw with a pencil. We will do that. Number 7. List all possibilities. Maybe hard to do for the full problem with 10 prisoners, but we can surely try this when we investigate simpler cases. Number 8. Learn from previous riddles. This one is the first one, so we'll have to do without this. Scrolling through the technical strategies in the same way, I believe there really are only 2 of them that can be applicable. One is parity, which is something that can be useful in the context of binary information. Things like 1 and 0, black and white, even and odd. The second is about thinking in terms of playing against an opponent in an adversarial game. In this case, it means that we have to imagine randomness playing against us, knowing our strategy, and doing everything to make as many prisoners as possible guess the wrong color. Okay, now we know what are the tools that we have available, and when we can, the best starting point is to reduce the problem to smaller numbers. In this case, it is not really helpful to reduce it to 2, as we know that the first one to speak cannot escape, and we also know that it's very easy for the second to save himself, if the first just shouts his color. Let's then look at the situation with 3 prisoners. Again, the first one to speak can only help the others, but how? Not saying the color of the second, as the third would have no clue, and not saying the color of the third, as the second would have no clue. Okay, so let's list the possibilities, and let's take advantage of the symmetry to get out those configurations that can be obtained by swapping all whites with blacks and vice versa, as they are effectively the same. But we can also ignore the color of the first, as we know that he's doomed anyway. Out of the 8 possible combinations, this argument allows us to start removing some of them. As we don't care about the color of the first hat, we can remove the last 4 configurations. In addition, we can swap the colors of the second and third hat, so that configuration 3 and 4 are equivalent to 1 and 2. We are left with only 2 possibilities. Second and third prisoners have the hat of the same color or hats of different colors. And what is interesting is that the first can transmit 1 bit of information, which means he can communicate in which of these 2 situations the prisoners are in. For example, they can agree a code where by saying white, what he really means is I can see 2 hats of the same color, and by saying black, I can see 2 hats of different colors. This is enough for the second to know if he has to say the same color as the one in front of him or the opposite. And after him, the last will also be able to know if he has to say the same color shouted by the second or the opposite. This way, 2 out of 3 are saved, regardless of how randomness is playing. Let's now try with 4. Our ambition here is really to save 3 out of 4, as we know that we can save 2 from the previous case. Let's list again. I will put an X to represent the color of the hat of the first prisoner, as we know it doesn't really matter. Compared to the case with 3 prisoners, we have now increased the configurations to 4, as we can still remove the ones that are equivalent in the symmetry. However, we also have increased the amount of information that each prisoner has. For example, the second prisoner can now see 2 hats. How to take advantage of this? Well, let's consider we are in one of these 4 cases and the prisoner has to help the second to guess the right color, which is white in this case, while still providing useful information to the others. We can start going down this way and take advantage of the fact that the second prisoner can see 2 hats in front of him. For example, we can distinguish the cases where the last 2 prisoners have the same color and the ones where the last 2 prisoners have different colors, as this is a piece of information that the second prisoner has. The rule they agree before the game could then be something like: the first prisoner will say the color of the second if the third and fourth are of the same color, and opposite of the second otherwise. Let's see how this plays out by looking at configuration 3, but you can try all of them. Third and fourth are of different colors, so the first says black, which is the opposite of the second. The second can see the 2 in front of him of different colors, and knows that he has to say the opposite of what the first said, so he will say white. The third knows, from the fact that the second said white, that he has the color opposite to the one in front of him, and will therefore guess correctly, saying black. Finally, the fourth also knows that him and the third have different colors, so he will just say the opposite of what the third said, so white. Looks like this works for 4 as well, and the key point was for the ones that come later in the line to also take advantage of what previous prisoners have said, on top of what they can see. But now we have to do the big step: how to generalize to 10 without having to repeat the process for all numbers. The question is, what have we been using for cases with 3 and 4 prisoners that can be expanded? To understand this, let's compare configuration 1 and 4 when we have 4 prisoners. In both cases, the first says the same thing, white. So what do they have in common? And what do 2 and 3 have in common which is different from 1 and 4? We'll leave you 1 second to think about it. Okay, I think you got it. Parity. Configurations 1 and 4 have an odd number of white hats, while configuration 2 and 3 have an even number of white hats. And if you think about it, this is really all the first one has to communicate to make all other prisoners guess right. If they know that there is an even number of white hats, they can just count the one in front, sum the ones that have said white before, and if it is an even number, they are black. Otherwise, they have to be white to make the total even. Is this limited to 3 or 4 prisoners? Not at all. It can be any number. This will always work. And so yes, 9 of them are safe, thanks to their logical abilities and to the sacrifice of the first poor prisoner. May he be remembered. Did you solve it? If you did, at which point of the video did you feel that eureka sensation? And would you classify this as an easy, medium, or hard riddle? Let me know in the comments down below, I'm really curious. If you struggle a bit, that is perfectly normal. It takes some time and practice, and the more you train, the better you will become at solving riddles and make these logical connections. If you enjoyed this video, make sure you press the like button, subscribe to the channel to get notified when our next riddle is out, and I will see you in the next video. I am Yuri, and this is RiddleBear, the channel that will help you develop riddle solving skills and be able to solve riddles you didn't think you were capable of.